Great to be here. I will tell you a little bit about the different pieces that we think need to come together for large-scale accurate simulations. And what we really want to do is go from really quantum accuracy, and by this I mean exact solution of the Schrödinger equation, and we want to do it at, let's say, million atom scale. And how do we get there is not so easy. You have to imagine breaking the problem into little pieces first, and we have to build on what's available. So the first thing that I'm going to talk about is efforts to improve the intermediate description, not sort of a wave function methods, but at DFT level, which are very practical for many applications, but they suffer from accuracy issues that prevent us from using these methods for large-scale accurate simulations. Okay, so the next step, once you have, let's say, a good density functional theory, which we're moving towards, the next issue is, well, drop the electrons and just concentrate on the ions and move them around at a much lower cost, as Gabor was explaining in great detail. And that's the domain of force fields, which we can also learn. So all of these are sort of learning problems. You learn from sort of the bottom up, right? Then the next step is once you have good force fields, you can run long MD simulations. But if you have some reactive steps or very slow dynamics, it's still insufficient. You can run for thousands of years without seeing the important stuff in your simulation. So you need to worry about reducing dimensionality of your problem and accelerating sampling of certain key things. I won't talk about it because there's no time. But then you can get to large-scale simulations. So this is the overall vision, overall the program of the computational material science or computational chemistry or biology. I guess any system that's made out of atoms would be applied here. Okay, so what's the picture again? So showing these trade-offs. What we want to do in terms of a method development is, first of all, we want to go from DFT scale, which is relatively slow, but still affordable for many systems, like 100, maybe up to 1,000 atoms. We want to take it to billion atom scale to have cheaper, but still as accurate interatomic potentials. It's possible with some machine learning techniques that have come to fruition over the past few years. And then the same thing we can try to do with DFTs. We can sort of learn from very, very accurate wave function theory and take it perhaps to a DFT level kind of scale. And then, of course, combining these two will allow us to achieve the goal that we want at quantum accuracy at large scale. Okay, so first section is on learning DFT functionals. DFT functionals have been around, of course, for decades, and we have this sort of Jacob's ladder construction, which goes from simple to more complicated descriptions of the electronic problem in terms of just local descriptions of density, introducing gradients to capture the variation of the density. You can have second derivatives or kinetic energy. Now, there should be Laplacian perhaps somehow here. And then you can look at hybrids, which mix some amount of exchange information in there, and so forth. You can sort of go up to RPA level correlation descriptions. So these are all being pursued, but they suffer from the trade-off of accuracy and computational cost. So there have been some approaches. None of them are perfect. Either they don't satisfy exact constraints that we know should be in the functionals, or they're too slow, or they only apply to molecular systems. So I won't go into the details, but this is something that's starting to become a little bit of a field. So a couple of people are thinking about this direction. I think it's very, very important if we want to make progress without assuming that current semi-local DFT, which is universally used, is correct. Okay, so what we want is, first of all, the question is, can we learn a functional that is something that we know about, an exchange functional? It's a non-local quantity. So something that's very difficult to come up with a semi-local model that's accurate. So the exchange energy. Okay, so we're just concentrating on the exchange energy because for many applications that's important. That's what you have in a hybrid calculation. You have an amount of exact exchange calculated explicitly and mixed in with your maybe semi-local functional otherwise. And the difficult part here, especially for solid-state systems where you have a plane wave basis set, which is not so easy to deal with in terms of integrals, is you have to compute this integral quantity. Essentially, it scales like the fourth power of the number of basis elements, as you can see from this. And so the idea is that can we actually learn it? Can we replace this by a much cheaper exchange model that is learned on something like not individual sort of orbitals constructing these integrals, but learned on the density. So that's the idea of constructing features from which we can construct a machine learning model that operates on the density only. So an explicit functional of the density that captures accurately the exchange interaction, which is an orbital-dependent complicated integral quantity, non-local at the same time. Okay, so the idea is that we construct a model for the exact exchange, for the exchange enhancement factor, which is basically just, this is a derivative. This is sort of a classical electron gas kind of result here. So the idea is that we want the model to be non-local, and we want it to satisfy exact scaling laws that we know should be in the exchange energy. Okay? So to construct a non-local model, we can use a kernel that's used together with a density to have some sort of non-locality quantification, and these features are then, constructed in such a way that we can also at the same time, from the very beginning of the sort of machine learning process, encode the exact scaling constraints. So this is an illustration for a helium atom where the density is the red. So as the density gets high, you see that the kernel here gets narrower, and so this is what happens to the feature. And the reason this happens is because of the scaling laws that have to be satisfied. So, okay, so by having this sort of kernel construction built to satisfy exact scaling laws that should be in the exchange energy, we're able to construct a machine learning model that knows how to treat different domains of density in a molecular solid. Okay? And the next step is construct a machine learning model itself, which can be done with a neural network, or in a more interpretable and sort of a smoother controlled way, you can use a Gaussian process regression where you can adjust hyperparameters to make sure that your features are smooth, which is very important for calculations, as we'll see. And so we take an approach that we used previously in the domain of force fields. Essentially, it's a sparse Gaussian process with a particular structure of a kernel. And you essentially then learn on some sort of a training set. The nice thing about exchange energy is you can compute it exactly because it's a well-defined integral. We basically evaluate a bunch of these integrals for a number of systems like molecules or solids, and then you can train a model that way. Okay? So this is an exercise not to sort of solve DFT in one shot. It's just the part that deals with the exchange energy calculation. Okay, so the training levels are again exactly available from various maybe bond dissociation energies, barrier heights, or atomization energies. These are calculations that have been done. There are databases available, or one can easily do them as well. Okay, and then we basically plug in a model, this machine learning model, into a hybrid functional calculation where typically what you would have is a mixture of some sort of a maybe PBE functional, a semi-local GGA functional, and then we put, instead of an exact exchange, we put this machine learning model. And the hope is that it will be much more scalable and much cheaper and can go to much larger systems than we can conventionally go with hybrid functionals, which have been shown to be much more accurate than semi-local DFT. Okay? And then we implement all this in DFT codes that are widely available and open source, both for molecular codes and for plane wave calculations, the GPO code and the PyCF, both Python-based codes that are easier to modify. Okay, so here's a basic summary of what kind of learning we are doing. The data sets are taken from large databases of molecular structures and energies and barrier heights and other kind of labels. So a wide range of different molecular systems go into the training, as well as some solids and specifically the cohesive energies. And some additional data points, but these are choices that you have to sort of make ad hoc. What do you train the function on? And these choices influence, of course, the quality of the model in the end, but you have to start somewhere. And the types of models we learn are either you could say, okay, I'm going to learn a GGA model, basically just the gradient goes in the feature description, and you can do a machine learning exercise just learning the best possible GGA model with a machine learning Gaussian process regression algorithm. In that way, of course, you won't get the best model, but at least you can see sort of what's important, what's not for feature selection. Then you can do an inclusion of non-local features that I talked about previously with this sort of kernel that's non-local, interacting with the density, and then you have a non-local description that also goes into the feature. Okay? And you can also have kinetic energy, which is an orbital-dependent quantity, but it has some nice physical properties. So you can include that in the machine learning model, or you can combine all three. And of course, we'll see that the best combination will be with all three included, and there are physical reasons why that is. Okay, so jumping on to the results. So you have this Gaussian process regression model. You can speed it up by certain mapping tricks. I won't go into detail, but this is the same thing that we've done for force fields previously. And this is a result showing that combining this kinetic energy density and non-local features actually is the best combination in terms of accuracy. You can see this green set of points here are the CIDR, so we call this approach CIDR. This is the benchmarks on the molecular systems. It shows that if you construct these kind of combined approaches, this hybrid approaches, essentially trying to mimic PBE0, which is this hybrid functional, then indeed having a non-local meta-GGA is the best performing on a molecular test set. Okay, so we hold out some set of molecules to this test error calculation. Okay, so on the solids, it's the same result. Essentially, you get the combination of kinetic energy and non-local features actually as the best performers for this machine learning model in terms of accuracy. And by the way, the accuracies here are quite good in the sense that they're mimicking relative to PBE0 essentially quite a small deviation. So they're able to learn essentially what PBE0 would give you for solids and for molecules. For molecules, maybe it's not such a big deal because hybrid calculations, or at least exact exchange calculations for molecules, have been quite optimized over the past few years with semi-local and adaptive compression techniques and so forth. But for solids, it's a big deal. Doing exact exchange calculations for solids is extremely, extremely expensive. So this is why you would, if you do a hybrid calculation, you pay orders of magnitude more. Yeah.
Why is the green a little bit bigger than the blue? Why can't you match PBE?
That's a good question. So this is a semi-local GGA machine learning model. So actually, I don't know exactly why it's a bit worse, and you could argue that you could try to. So we didn't do very much optimization trying to get the best possible GGA ever, right? So PBE is pretty good. Okay, so if we wanted to go to great lengths, including sort of a lot of engineering to the features for just the gradient, maybe we could have done better. But I don't know exactly why. That wasn't the target. Okay, the point is that we can do much better with a combination of non-local and, but yeah. So no great answer there. Okay, so, all right. So this is a set of results on.
You had a comment about this. These are non-self-consistent results. I didn't understand what that meant.
So these are taken from orbitals that were computed with PBE, and then we basically do the calculations on top. Yeah.
So going back to the same question. So do you have a sense of what the density-driven error would be? Because your target is the functional-driven error that you're trying to minimize. But do you have a sense of what the density-driven error would be?
No, not really. I think it requires a careful investigation what the density does. So yeah, training on the density is non-trivial, and this is definitely something that we'd like to try in the future if we can find a cheap enough way to do it. The training was done on the energies, total energies. In fact, in the first version, we tried on exchange energy density training because you'd think that having local information on exchange energy density would make the model smarter, but we didn't actually find that much benefit to doing that compared to the total exchange energy being the training label.
But even as a post-processing step, was the error assessed against a more high-level calculation as to if you do the self-consistent calculation, the density that you get from this newer.
Yeah, that's something we really want to do, but we haven't done yet. Yeah, that's a good question. How much do you get actually the density? We were focusing on the energy errors. Yeah, that's a good point. Same question? Okay, good. All right. Yeah, so this is results on GMTK and 55 molecular systems that basically shows that we are significantly beating semi-local DFT, and as I'll show later, it's not any significant additional cost. Okay, so in this case, we actually started with a pretty advanced hybrid functional and swapped the exchange part with the CIDR model, and we compared with the actual reference values, which are higher quantum chemistry calculations or experiments were available. Yeah.
I know you're doing something different and perhaps more transferable than learning the force field. But what happens if you try to learn the energy difference between the PBE and the PBE0 as a correction to the forces? Because ultimately, if you want, right, because your test, this allows you to get other things. You're doing a DFT calculation, you're getting densities, you can get other things. But if you're testing it on energies and forces, it's sort of natural to ask, what happens if you just actually fit in one of your forces?
That is a good question, and I guess there's only one answer to try and see. My expectation would be that you could probably learn force errors quite accurately with a delta model like that. But of course, that's just forces, as you said, and you won't get band gaps or anything that might be of interest from DFT point of view. But yeah, it's a good question to try.
Because this is learning something, a very physical quantity that's different. You may extrapolate better than.
Yeah, transferability probably will be better. Yeah, but that's a good question. How? Yeah, I mean the goal here is to do a universal exchange function. In other words, all the molecules and some very sort of diverse kind of solids, but not very many solids go into the training. So, but that's the goal. Is not to be system dependent like we typically do for force fields. Okay, so kinetic energy is something that's important, and here's the physical reason of we think why. If we think about the kinetic energy, it does have a derivative discontinuity sort of built into the description, right? If you only operate on the density itself, any sort of change in the number of electrons is not going to introduce any sort of non-smoothness if you have a smooth function of the density, right? You cannot possibly have that. The kinetic energy does have a derivative discontinuity, and that explains why meta-GA functionals, which operate on kinetic energy, often have better spectral and sort of band gap predictions. And this was the inspiration that if we build this into the model, then there's going to be some sort of the ability of a system to capture the change in the number of electrons, and this would be an exchange energy model that would also have some derivative discontinuity behavior. And we test that, and we find that yes, indeed, if you change the number of electrons, like by looking at these toy model systems, just a helium atom, starting with triplet, singlet states, and so forth, changing the number of electrons, we see how the different models perform, and we do find that the meta-GGA with the kinetic energy mixed into the description in the machine learning model is able to significantly better capture what the energy differences should be upon adding the number, upon adding an electron. At the same time, this kind of model systems, like trimers and dimers of hydrogen atoms compared to the monomer, allow you to test different localization of the charge density scenarios. And test how much non-local features are important. And again, we see that non-local models do noticeably better than semi-local models at the fixed number of electrons. So these are sort of the two things that can help you rationalize why you need non-local characteristics in your exchange model, as well as a piece that captures derivative discontinuities. Okay, so this is a result on band gaps. We of course care about band gaps in a lot of DFT calculations, and here is a result showing that the mean error, the mean absolute error here, compared to experiments in a set of 261 band gaps, we selected those that don't suffer from spin-orbit coupling kind of results. If you include those, and sort of start questioning some of the references. But at least on this set of different semiconductors and insulators and so forth, we see that we are starting to approach PBE0-like accuracy. And this model, of course, is supposed to mimic PBE0 at a much, much lower computational cost. And of course, it does much better than any PBE and competitive with things like SCAN, which are also sort of semi-local models. So band gaps are becoming better with these models, and that means that you can do sort of larger DFT calculations at a much lower cost. And this is the cost comparison. So, if you do a PBE0 just straight up with a 216 atom diamond supercell, so again, a periodic system with plane waves is going to be an issue for exact exchange calculations, as of course the scaling is very unfavorable. So we see this is a log scale plot, how much more expensive hybrid calculations are compared to, let's say, PBE or SCAN type models. And here's where CIDR models are. So they're sort of comparable, right? But you get essentially the benefits. And what are the reasons for doing large-scale DFT calculations? So, well, a lot of cases involve things like defect formation energies or defect transition levels. So if we look at one example case for silicon, where, of course, the band gap is a problem when you try to do transition level calculations. The defect levels, of course, not going to be very good agreement with experiment. And CIDR, being sort of the surrogate for a hybrid model, does much better and much closer to experiment. So because the band gap is fixed more or less, and your defect levels are in better shape. And by the way, defect levels require some significant computational cost otherwise, because the sometimes the defect charge is not very localized. You need large supercells, and this is where hybrid calculations are unaffordable but necessary if you want to study accurate electronic structure of defected systems. So, and we have in the paper, if you want to see some more different types of defects, not just vacancies or different types of substitutions. Okay, so the summary is you can achieve hybrid DFT kind of accuracy by doing a machine learning on at least the exchange part. And you need to include both the kinetic energy and non-local information into the machine learning model. And you can enable large-scale self-consistent calculations within available DFT codes with these models with efficient implementations and worrying about putting this into the PAW, formalism, and everything. That was done by Kyle, who led this work. And that also opens possibilities now to use this feature set and to use this procedure to also learn the full exchange correlation functional. But there are sort of conceptual questions, how to select reference training data, whether to include densities, which I think would be very important, and so forth. Okay, so this is something that sort of lays the foundation of what could be done, at least in the field of DFT itself, where much improvement is still needed. Okay, so suppose we solve this DFT problem at some point in the near future, then we need to do large-scale simulations with machine learning potentials to do something like heterogeneous catalysis on complicated systems. We need to study reaction networks, which are not very easily described, perhaps intuitively. And we can also study dynamic phenomena where the catalysts, in this particular example, react in shape changes and restructuring and surface reconstructions to the chemical environment itself. So these require explicit large-scale MD simulations. In the biology field, it's the same issues, right? You need atomic level resolution. So this is where we sort of try to go with a molecular dynamics approach. I won't spend time here because Gabor already explained everything. Machine learning force fields are the answer. The type of machine learning force fields that we have been focusing on over the past few years are what we call sort of symmetry-aware, in the sense that we start with some sort of a description, a local description of a atomic environment. So we say, let's see what an atom sees around it, and there is some sort of a set of atoms in the neighborhood that we need to know where they are and what type they are. So we build some sort of a description. From the description or representation, as we can call it, you can do machine learning in different ways and obtain a local energy, which you can sum over and get it to global energy, and then you can differentiate the global energy to get forces, and then you can run your molecular dynamics. Okay, so this is the way. And we've been developing two types of models, one based on equivariant neural networks. I'll explain a little bit what they are. And the other one is based on Gaussian process regression that's built on top of descriptors. So very similar to what I was talking about for functionals, but now in the domain of representations of atomic environments. Okay, so the symmetries, again, that we want to build into the system are dictated by the Euclidean group. So this is a set of rotations, inversions, translations. So essentially, what we want to have is a model that is aware that our materials live in 3 dimensions and obey the Euclidean symmetry group, as well as some sort of chemically motivated permutation symmetry. Okay, so what are equivariant models? Equivariant models are models that are neural networks, but instead of being scalar, like using vision or natural language recognition, where you essentially have some sort of a feature that goes into an MLP, and then you have lots of nonlinearities acting on it, and you get, let's say, something like an energy output. Instead, we construct a neural network that has features inside the network that transform like vectors or tensors, and that means that if you rotate, let's say, your input, the features, that if they're invariant, they just stay invariant. They're scalars, like distances or some sort of angles. In equivariant models, these features also rotate, and then you can build your entire model whose internal representations everywhere have this essentially commutation relation with the with whatever's happening in terms of operations inside the network, commuting with an operation that acts on the input. So this is what equivariance means in sort of mathematical terms. And there's been, of course, some intuition initially why invariant models based on only distances are insufficient to capture the full geometry. And again, Gabor explained that there's sort of this missing kind of information in distance-only models, like, if you build a neural network with this machinery out of only distance information like Schnet, you will miss something. So they're supposed to be better. I mean, historically, why we did this is because we wanted to build force fields that are just sort of predicting forces. So that was the initial motivation. I was thinking, can we build a model that just goes straight to the forces and that requires you to have a vector-valued neural network? And of course, we realized there are some issues with that, but the machinery sort of just became available in some equivariant neural networks, at least the layer architectures that were published. So we built upon that. And the sort of generalization of vectors to higher order tensors using spherical harmonic embeddings and things like that led us to this NequIP architecture, which was the first equivariant neural network, which was message passing. In other words, all the features are some sort of collection of tensors of some rank, and then that forms messages that are passed around between atoms, and there's some convolution operations based on tensor products that make a more complicated kind of way of combining information and capturing many-body correlations. Okay, so we're essentially asking the neural network to learn the representation using its ability to operate on equivariant quantities. So this is what sort of deep learning is about. You give a model a representation rich enough and aware of symmetry, and asking then the model to sort of train on some reference data, and somehow under the hood it will learn the equivariant representations. And so this doesn't require us to actually form the features explicitly.
Ask a simple question, just for clarification. Are you learning, so I think you mentioned both energy and force, right? So are you learning the forces only?
You could. Typically what we do is we learn on forces, total energies, and stresses at the same time. Yeah, so the way this works is that you have a model that is just predicting energy, and then you backpropagate through the model to get the forces, and then you could do similar things for stresses. And then you can have a loss function that depends on all three quantities, and you have to adjust the weights of the relative sort of loss.
What happens is that when you have a small cluster of atoms, you can define the forces on the atoms that are in the middle. How do you separate the energy from the rest of the system?
So that's a good question. So the total energy is well defined. Let's say we take as a reference DFT calculations. They have total energy as an outcome. This is the whole formalism of DFT. You have forces from Hellman-Feynman. So those are very well-defined physical labels. Local energies assigned to each atom are not physical, not well-defined, and they're just intermediate quantities. And this goes back to the original Bell-Pernello ideas of partitioning your model in a local kind of set of environments whose sum then is supposed to give you the total energy. So whatever model learns under the sort of this procedure for local energies is not very well understood or very well even formulated. It's something.
My only worry is that if we only learn forces, can we guarantee that the force that we gave to MD is still conservative?
If we go for a direct force prediction, no, unless you have some sort of a constraint that enforces a curl equals zero condition on the force field. But this is automatically guaranteed if you go for a scalar like energy, because then it's a gradient, and the gradient has automatically curl zero. So if you go for a prediction as total energy, as the sort of final outcome of the model, that's guaranteed to be energy conservative because, the steering will apply. Yeah. Okay. So we have some sort of a tensor algebra going on as the layers sort of propagate information between the atoms. And in the end, all these sort of message passing operations based on tensor products give us, let's say we have 6 layers or so, we get a final scalar energy, and that's the basis for all our sort of training and prediction. Okay, so, and these kind of models have been shown to achieve state-of-the-art accuracy at the time. This is a set of molecules and dynamics on molecules and energy on various molecules, and we see that equivariant models are quite competitive. If you go to, let's say, rotation order of spherical harmonics being 3, then you get very good accuracies compared to previous models. So the inclusion of equivariant kind of information seems to be important. Plus, you also find out that the models learn very quickly, which is represented in the if you look at the scaling plots of how much error is as a function of how much training data you give to the models. They're qualitatively different from previous types of models. So there's advantages in both learning efficiency and accuracy. And this is demonstrated by this comparison with the DeepMD model that has been one of the first deep learning models in the field. And this is comparing with training on water and ice kind of structures, where DeepMD requires let's say 133,000 training points to learn, and then the error is still larger than the NequIP model with only 133 structures. So 1,000 times less data gives you lower errors due to the equivariance. Okay, so, and then I think Gabor already mentioned there's this sort of interesting behavior that they're also smooth and transferable, also as a result probably of their better ability to learn. And this is a magic of deep learning, which is hard to understand and to rationalize, but we take it when we get it, so it's useful. Other kind of empirical sort of results on these kind of models done by other groups, in this case it's an MIT group led by Tommy Jakola, established that for machine learning force fields, especially if you use them for molecular dynamics, it's very important that they're stable in long-term MD simulations, because this is what you want to use them for. And if neural networks are maybe insufficiently trained, or maybe have some sort of non-smooth kind of outputs, that creates a problem. And this is always a worry, like if you use a over-parameterized model, is it going to be really smooth in the domain and maybe a little bit outside of the domain where you're doing MD simulations? So in this case, NequIP was the only model that was able to run whatever benchmarks on various systems that they were trying to investigate. Okay, so that is all encouraging. There's a big issue with these message passing networks in general. I think there was a comment in one of the first talks. What happens to this effective cutoff? So we're talking about local representations, but then we have these messages passing between atoms. So atoms talk to other atoms through, let's say, 6-angstrom cutoff locally. You start talking to, let's say, atoms across 2 layers. You already have like a 12-angstrom cutoff, so this is potentially already hundreds of atoms. It gets quite expensive. If you have a state-of-the-art model in terms of accuracy, in some of these benchmarks 6-layer models already have 20,000 neighbors that you need to worry about. And then imagine putting this into an MD calculation. Well, then your neighbor list's quite massive, and parallelization becomes incredibly difficult. So you really can't parallelize these models on more than one GPU. And it hasn't been possible to my knowledge. So this was the idea, to go back and see, can we do a strictly local model that still is doing something that NequIP is doing? And what it's doing is passing messages between the atoms, capturing many-body kind of information, even though messages could be quite low body order in the beginning. But you could reformulate this, either sort of including, as we were thinking together with Gabor, higher order messages themselves, and maybe that requires less hops then, okay? So, or you could do it various other ways. There's many ways of doing that. One particular way that we investigated is to put, features, instead of putting them on atoms, putting them on edges, making sure that any sort of convolution operations only touch edges that, connected to the central atom, and information never propagates outside the strict cutoff radius. So this allows you to capture many-body information with equivariance without having message passing. And this is the Allegro architecture. This essentially the idea that you have some sort of a scalar information in the network architecture, some tensor information. They, of course, exchange various sort of couplings and information as the 2-track architecture is operating. But in none of the layer operations, you're allowing information on one edge to propagate to an edge that's not connected to the central atom. Okay, so this is the idea, essentially. You have a central atom, you have some features, which are, again, some sort of spherical harmonic embeddings initially, sort of encoding equivariant representation information, and then you have tensor product operations that connect only to edges that are touching the same central atom. So the information stays strictly local, and it can be done quite efficiently using the density trick that Gabor talked about, and we got inspired by that. And this is essentially the idea here is to sort of combine this tensor product operation. You only need one tensor product to essentially interact with all the other edges in your representation. And that can be built into a neural network model that is also equivariant, but now strictly local. And you ask, is it doing anything worse than NequIP, which was sort of this original idea? And the answer is really no. It's doing quite well, maybe in some cases very slightly worse, some cases slightly better, but this is already getting into sort of hair-splitting kind of situations. Where is it better, where is it worse? So this is just sort of to show that it does achieve state-of-the-art compared to many other models, and it does combine the strict locality with equivariance, and thereby achieving very good accuracy. Okay, so now we have locality, we can scale it. That was the whole point, to massively parallelize and take it to exascale. And so this is now showing on a log scale the number of GPUs on which the model is deployed, and some sort of examples for a material. In this case, it's lithium phosphate glass, kind of a complicated material, and we study dynamics of diffusion through it, making sure that it agrees with DFT, but then taking it to much, much larger scale, going up to tens of millions, and maybe now, you could do 100, it depends on how many GPUs you have access to. You can deploy these models on very large numbers of nodes and take advantage of leadership class computing that are all GPU sort of heavy. So these codes are significantly optimized for running on NVIDIA GPUs and taking advantage of such resources like Summit or Perlmutter and things like that. Okay, so you can get very, very high accuracy, essentially state-of-the-art accuracy in terms of sort of what's available in force field world, and then at the same time, the scalability and the local representation allows you to do these kind of massive calculations. Okay, so this is good if you have a good training set. Again, goes back to, is your DFT good enough? Is your training set itself good enough? Covers everything that you need to cover? So that takes me to the question of selecting the training set or understanding uncertainty. So far, we haven't talked about uncertainty. We started doing that for neural networks, but it's really far from great. So you'd rather have some sort of uncertainty measure, or in other words, a distance metric in your representation space between your configurations that the model hopefully can deal with and understand and being able to predict. So if you have that, then you can actually have your model train on important points, and not just points that you throw at it without any sort of bias. But if the model is able to recognize that certain points, let's say in this transition sort of state far away from equilibrium states, are new, it should complain, and it should at least not provide a believable answer, right? It should come with some sort of degree of uncertainty. Okay, so how do you build uncertainty quantified models? You can start with descriptors and build a Bayesian model, a linear Bayesian model, or you can build a nonlinear, like a Gaussian process regression. This is what we do. We can start with various many-body descriptors. In this case, we started with the ACE. It just came out at the time. Ideas from, again, as Gabor mentioned, Ralph Draus's group. And these ACE descriptors can then be, so these are equivariant quantities that you can then contract to form invariants. And then out of these invariants, you can construct a kernel function using, let's say, dot product operations. And then you have a Gaussian process regression that now predicts not only the means, which are forces, energies, whatever you want, but also the posterior distribution. And you can take the variance, and you can quantify the uncertainty that way and say that, if descriptors are very different, the kernel will know about it and will tell you that, there's not much information in this term, and then the variance would be high for points which are far away from the training set. Okay, so this is just standard Gaussian process regression based on kernels that are based on some sort of many-body descriptors that are hopefully complete, like ACE. And you quantify this uncertainty by doing a correlation with the test error itself. It's important. In some cases it's good, sometimes it needs to be rescaled. So this is still much to be improved, this kind of uncertainty quantification, but is of course better than nothing. and it does correlate with the true error in many cases. So when you have that, then you can do active learning. That's the idea of the flare code that we developed, which essentially is a way of doing molecular dynamics now by learning on the fly. So you basically started an MD simulation. You could even start with no knowledge of the force field, and the model would just have high uncertainty everywhere. And every time it has high uncertainty, it would call a DFT calculation, add the configuration to the training set, take another step, and see if the uncertainty is high or not. And we'll continue doing that until you find out that the model has seen enough of the configuration space to not ask for DFT anymore. And this is what we see in many cases as the loop is progressing. So at a certain size, which you can still go back to DFT, and this is an important point, you could do this active learning and then simulate a system. Like in this case, it's a 2D material, stanene. So the question we're asking there is, I think related to the previous talk, are these sort of 2D materials, are they stable, are they fragile? What happens when you twist them, put them on substrates, heat them up, these kind of things. Very difficult to do experimentally, but you can do a simulation of a stanene sheet trained on just pure bulk stanene, just a 2D lattice, it's kind of like graphene with a little bit of buckling. And then we see that there's an uncertainty that all of a sudden increases at a certain time during the simulation. And you go back and you see high uncertainties, these are sort of yellow-colored atoms, are the ones that pop out of the layer. And that happens at pretty low temperatures, experimentally speaking. And so you can continue running these simulations, and you see that at a certain time, again, there's sort of this destruction of the layer happens, uncertainty spikes, you can retrain and sort of proceed until you actually have covered the entire configuration space that is important for capturing this stanene. So this is a result of this kind of simulation at now large scale, many atoms, essentially investigating how does a 2D material transform and melt. And you see this disordering, and it's even at 500 Kelvin already sort of starts breaking and turns essentially to a blob of liquid. And then the liquid has a necking kind of phenomenon going on, and it merges into one blob. And this is all sort of DFT accurate kind of large scale MD simulation, which allows you to look at what happens in this material. Far from the stability of graphene, of course. It's actually quite fragile. Oh, this is another simulation at a lower temperature now asking, what if you reduce the temperature, it's still going to melt? In this case, if you look at the beginning of this movie, it doesn't, so it still sort of ripples. And then there is some sort of a transition going on. It turns into this disordered multi-layer structure, which then recrystallizes at bulk tin. So this is what happens to stanene at 200 Kelvin. So that maybe explains why it's been very difficult at room temperature to have any sort of freestanding stanene layers in general. Okay, you can do calculations of phase transitions with this approach now. Anything you sort of can do with an accurate machine learning force field these days. Again, tracking uncertainty as you pass through a phase transition, as you increase the pressure on this material. Silicon carbide goes from a zinc blende to a rock salt structure. You have some sort of uncertainty spike, you retrain, and you're able to then reproduce experimental data quite accurately with a resulting force field. And then you can crank up the temperature and pressure even further, covering essentially insanely high temperature and pressure conditions to explain what would happen if you take silicon carbide and just at high temperature, at high pressure, measure what the phase is. And there's a question in experiment, does it actually melt or does it decompose? So this is a debate that's been going on for years because it's extremely difficult to make such experiments. And so the calculation that we did shows that in case of silicon carbide, it actually decomposes. And there are these sort of diamond and graphite-like inclusions that form. That allows us to predict the entire phase diagram of silicon carbide to see that there's a decomposed phase between the solid state, which is in this case the zinc blende structure here, the rock salt at high pressure. You increase the temperature, there's a decomposed phase where the silicon is molten and carbon is a solid, like these inclusions. And then, of course, if you heat it further, you melt the whole thing. And so this agrees with some available experimental data, so allows us to essentially do these kind of phase diagram calculations with these methods.
Does your 2D work?
I'm sorry?
There's in your 2D, that layer, there's this, I'm sure some of the physicists can help me out with, there's this theorem that 2D materials are not stable to long-range fluctuations, or Holmberg theorem, or who maybe some...
Norman Wagner.
Is that the one?
Yeah. Mm-hmm.
Okay, there you go. Is that related to that theorem?
Maybe. That's a good question. I mean, that's a strictly 2D kind of system, right? Essentially, it tells you that a 2D material cannot have sort of a thermodynamic stability. But here we're relying on out-of-plane deformations, which may modify the assumptions. So that's a pretty restrictive theorem, which I think may not, strictly speaking, apply here. Yeah, we discussed this with David Merman. Okay, no, let's see what, oh yeah, all right. So, sorry, David Nelson. I was going to say David Nelson is working on these buckling phenomena and rippling phenomena. So we don't know exactly what the connection is there yet. All right, how am I doing on time? Oh, okay, let's try to speed up here. Just to quickly show that, if you have good force fields, you can also do thermal conductivity calculations with Green-Kubo approaches. So this is another area of application that has been otherwise difficult if you want to rely only on first principles kind of approach. And you can use either Boltzmann transport or Green-Kubo and get thermal conductivities for complicated materials that way. Surface reconstructions is something that we, for the first time, can do now at large scale, looking at like gold 111, herringbone patterns that are forming just spontaneously in a D-simulation, something you cannot do with an EM potential. It has at least not been possible. And we get structures that essentially mimic what happens in experiment. And we can do it for many different indices as a function of strain and temperature. So essentially looking at surface phase diagrams with these force fields. And they are luckily very accurate for metals like gold. Looking at catalytic kind of fabrication. So if you're asking, how to make a catalyst that has sort of a magic combination of activity and selectivity for certain hydrogenation reactions, you want to mix metals in a bimetallic catalyst, and the way chemists do it is by depositing, let's say, palladium on silver is one example. In this case, what they were doing is depositing palladium and seeing that the initial islands over minutes of annealing time became thicker and actually etched away the first layer of silver. And this was not very well understood. And we did a simulation with flare to see that essentially the whole process starts at the edges of these palladium islands. And there's some sort of a transformation of the islands at some point to a two-story structure with this 50-50 roughly mixing, which is also what spectroscopy tells us here. And then as the islands sort of evolve, they start sucking silver out of the first layer, sort of forming these, you'll see in a second, pits that are etched away from the silver surface. So all of that from a sort of DFT-accurate MD simulation happens in about 2 microseconds. So what these MD simulations can tell you, not only the mechanisms and sort of what would happen when you try to make a catalyst like this, but also the time scale, which is very different from you could possibly measure experimentally. Because these STM scans take a long time, so you cannot resolve a 2 microsecond time scale information. So also you can do these reconstructions. Nanoparticles, what I wanted to show really quickly is that there are certain metals, as we discovered while doing sort of this catalytic kind of investigations, which are much harder for machine learning potentials to learn still. And we need to understand why and how to improve the situation. The metals like gold, silver, copper, and sort of these platinum group metals are quite accurately captured by NequIP and also FLAIR, which is based on this ACE representation. But regardless of what type of model you use, and these are very different models, like one is a neural network, the other one is Gaussian process based on descriptors, the trends in terms of chemical space are very similar. And we've done to great lengths convergent DFT calculations here. We see something systematic and something that tells us about the physics of metallic bonding, how much more complicated it is in early transition metals due to partial sort of filling of d orbitals, and the extreme sensitivity of angular deformations and many-body interactions between metals here that is still rather difficult for machine learning models to capture, despite all the progress and all the very low errors we get on organic molecules. These, I think, are the most challenging problems if we want to sort of further increase accuracy of these models. This is what needs to be solved, and this is an open question. What is required? Perhaps more intelligent ways of capturing many-body information as a function of radius of interactions. Okay, so this is sort of just a hunch, but this is something where we need to do a lot of work. And it also tells you that these models converge rather slowly with this rotation order, which is the rank of the tensor that neural networks, which are these state-of-the-art accurate models, are using, which means that angular information is still difficult to capture accurately. So especially for things like osmium, it still keeps going even to, let's say, a rank of 6. And when you have a 6th rank tensor in your neural network, the model becomes extremely expensive computationally. So let's say doing a large metallurgical level kind of calculation with an NequIP or Allegro model for a metal like titanium, even single element or osmium, is still going to be very, very expensive if you have to go to these higher rank tensors. So a lot more is still needed here to improve the state of the art. Okay, I think one of the last things I want to show is reactive systems. This is the whole reason why we were looking at sort of machine learning force fields, because there is no alternative really that allows you to do large-scale reactive simulations. And as a first example, we looked at hydrogen activation on platinum, a very well-known, rather fast reaction. And we can see a lot of in an MD simulation, hopefully. And this is the process. Hydrogen molecules attach themselves, dissociate, run around, then recombine. Hydrogen atoms will form hydrogen molecules and detach. There's some turnover that happens here. And there are certain questions, what kind of mechanisms are at play when the coverage is high? I mean, for a single hydrogen molecule, you can do a DFT calculation and see all the energetics you need to see. The complexity comes from high coverage, which happens in high pressure scenarios. And this is you can only do with an explicit MD simulation. And so this is what we did with this active learning approach using FLAIR as an example. These are the red atoms showing high uncertainty configurations, and these are the DFT cell that actually is being used for active learning. So the model starts with essentially no knowledge, calls DFT. A lot of times in the first few hundred steps, you see these black dots. This is then the frequency of DFT calls decreases, and essentially then we are able to learn what it takes fully automatically. So there's no human intervention here. There's only one step of human intervention. I'll explain a little bit later. But essentially the model learns on its own the platinum-hydrogen interaction with this kind of simulation. And it does so in a few days. If you parallelize, of course, it will be much quicker, but we just did sort of a serial kind of calculation in about, 300 DFT calls or so. Here, and overall about 500 DFT calls is what it takes to describe the reactive heterogeneous catalytic process of hydrogen dissociation and recombination of platinum. And most of the learning actually does happen in this kind of model, not the bulk platinum or hydrogen gas, which is also used here, but they are much, much fewer DFT calls for those. Okay, so here, what we did, we increased the size of the simulation after training on DFT to actually measure, as you would in an experiment, how many molecules broke as a function of time. So essentially just measuring reactivity and changing the temperature. And then we see, in this sort of plot, number of course, reactive events as a function of time increases linearly, as you would expect. Different slopes allow us to do an Arrhenius kind of analysis and to extract the activation energy and then compare to experiment, which is the ultimate test of whether your calculation is meaningful or not. And this is telling us that, first of all, the force field is accurate and that the DFT itself is accurate, which is often a challenge in catalytic scenarios. So this is something that, is far from obvious or automatic in many different reactions on transition metal surfaces where DFT can spectacularly fail to even describe adsorption geometries. So, and then we took it to a much larger scale, just to, again, illustrate how scalable machine learning models in principle can be with a sufficient amount of engineering of, parallelizability and, combining these kind of calculations of ACE descriptors with COCOS, which is this portability library that allows you to use any type of GPU, and making sure that GPUs are used very efficiently. This allowed us to scale these kind of simulations on the entire Summit machine to reach a scale of about 1 trillion atoms or 500 billion atoms here for the reactive simulation. And when we were doing this at about 1 million atom scale, we saw certain things that were not physical. So this is what can happen with these things, right? You train them, you think you're done, you think you've covered everything in the configuration space, you do a large scale simulation. At large scale, things show up that not necessarily show up in your small scale. And then at the million level, you see that sort of occasional platinum atoms were desorbing from the surface and flying away. So at that point, of course, you would think, okay, so what do? You can take a 1 million atom simulation, put back into DFT. So we increase the temperature. This is what the human intervention step was in this case. We increase the temperature and retrain it with these asterisks at higher temperature. So we have additional data, and the model got fixed by that, but that's luck, all right? So it might not happen in other scenarios, which are much more complicated. So this is one of those use cases where large-scale DFT, I think, is very important still. If you want to do active learning and you want to go back to larger scale reference calculations, there's really no option of just taking a little piece and putting it in DFT. You have to do a large-scale calculation, and DFT codes at scale can be very helpful here. Yeah?
If you do 200 atom simulations in parallel, just independently, put in the statistics, and one of them you would have seen the
Probably yes, but we didn't know it was wrong. So we only saw it when we actually, yeah, so if you think that, yeah, so maybe that could have been the strategy. But in some cases, it's not an option. So
I'm driving at the size of the simulation didn't bring you new physics, I thought.
No, it did not. In this case, it did not, absolutely. This is just scalability, like, for these kind of Gordon-Bell problems, right? You essentially just show that you can scale. Science is secondary. So in this case, it was not necessary. Yeah. Okay. So when it becomes necessary, it's like biological systems where you have large structures you cannot really divide into little pieces. Okay, so I'll skip that maybe because I'm short on time. There's some other results which are related. But what I really want to show is this one. This is an example of a battery calculation. So it's a solid-state battery phenomenon that's happening at the interface between an anode and electrolyte in this case. And there's some decomposition at the interface, which is observed experimentally as a battery is aging and cycling. There's some resistance built up. There's speculation of what happens. So these kind of simulations are probably the only way to really probe what happens at buried interfaces with electrochemical systems like this, where a lot of new phases are forming that maybe we don't know ahead of time. So these need to be large scale. And these cannot be split into little pieces that can be run in parallel to discover failure modes. And so this is where we see uncertainty of certain atoms is still high, even if we trained it on a smaller system. And it would be very nice to be able to put this sort of big unit cell back into DFT to fix some of these issues here, and then maybe have a more reliable model for reactions of interfaces. And again, this is interesting because here, this is happening already in 1 nanosecond. This is something that is very useful for battery community to understand, is that decomposition at interfaces in solid-state batteries can happen extremely quickly, and you can see what kind of phases are forming. You can sort of analyze all the soup that is here, and then characterize its electronic and ionic transport properties and so forth, and see how it saturates with time, whether the battery will survive or will just completely get destroyed by this kind of chemistry. Okay, I think with that, I will just finish with thanking all the students that contributed to this work and the funding agencies, and thank you for your attention.